Okay, there was some issue with the recording. It has just started. So, okay, I'll briefly uh, again repeat what we did so far. For part, for the first question, we were supposed to find the unity gain frequency, right? And how did we obtain that? We took the product of our open loop bandwidth with the open loop gain that gave us the unity gain frequency. Okay, the first one was pretty straightforward. I think there was nothing much to repeat there. For the part second question, we were supposed to find the closed loop 3 dB bandwidth, right? That we obtained by dividing omega t by 100. That was 10 to the power 7. That is around 10 mega radians per second, right? And since then, we were going through this third question, right? So what was Q3? Yeah, Q3, we were provided a voltage follower circuit, right? We were given slew rate, we were given uh, unity gain bandwidth, and we were supposed to compute the rise time, right? TR from 10% to 90% for four V inputs, right? In the first one, your V input is 50 millivolt U of t. Second one, it's 100 millivolt U of t. Third, fourth are 1 and 10 volts U of t. Okay, since this is voltage follower, V output would be V input. So likewise, we'll have same V outputs as V inputs, right? And how would we find the V max? Because we need that for the rise time, right? Because only then this 90% would be zero point 0.9 times V max. This 10% would be zero point 0.1 times V max. Your V max is slew rate divided by unity gain frequency. Okay. And that for this case is zero point 0.5, right? Because there is nano here and giga here. So this is zero point 0.5 volt, right? Your VI max would also be zero point 0.5 volt. And since we have this U of t, right? If you analyze it in Laplace domain and convert it back to time domain by inverse Laplace transform, you'll have this factor, right? E to the power minus omega tt, right? Where this omega t is what? Unity gain frequency, right? T 10% would be 10% of V output. And likewise, I'll replace T by T 10%, right? Because at this time instant, my V output is 10% of V output max. Likewise, I'll compute T 90%, where I'll replace this T by T 90%. And my V output would be 90% of my V output max, right? And likewise, then I'll go on to compute T 10% and T 90%. And once I'll have that, I'll need to compute the difference, delta T, which would be T 10% to T 90%. And that would be 2.302 nanosecond minus 0.10536 nanosecond, right? Because I converted this pico to nano, right? Factor of 10 to the power 3. Rise time comes out as 2.2 nanoseconds, right? Similarly, I then went on to say that you will do it for these three cases, right? This one I did. You'll do it for these three cases. Okay. I wrote the answer. You'll verify them at your end. Okay. Just give me a couple of minutes and then we'll move on to the next question. Sorry, I had to repeat it again because recording was not in progress. So, I mean, uh, I guess it is recording right now. Is it? Can anyone at least confirm? Yeah. Thank you. Just a couple of minutes and then we'll start the next question.
भाई सिलेबस कुछ दे नहीं रहा।
Can anyone confirm? Yeah, I guess probably on my level. I'll proceed, okay? So far we have done 3 questions. Now we'll see question number 4, okay? Question number 4 is as follows. I'll need to first draw the circuit for this question. The output. This is RF. This is R1. Okay. This is grounded. This is grounded as well. And this is IB1. And this is IB2. Okay. Now consider following. Consider that your IB1 is equal to IB2, and that is equal to 10 nanoamp. Okay. What is the output voltage for which your RF to R1 is having particular 3 values? Let me write them down. First case is your RF to R1, that is 10 kilo is to 1 kilo ohm, obviously, right? And likewise, part 2 is that your RF to R1 would be what? Uh, let's say 100 kilo to 10 kilo. Okay. And the third one would be your RF to R1 would be 1 mega to 100 kilo. Okay, 1 mega is to 100 kilo. Yeah, that is what this would be. Now, how will we proceed on this one? We need to find the output voltage, right? And your output voltage would be anyone? What is V output? It would be IB1 times RF, isn't it? Right? I mean, doesn't it make sense? V output. This is virtual ground, right? So V output, this is V naught minus 0 divided by RF is your IB1. So by that, V output has to be IB equal to IB1 times RF. I hope it's clear. So, I mean, it's given that your IB1 is what? 10 nano, right? Now, if your RF is 10 kilo, right? For this case, it's 10 kilo, right? What is V output? V output would be what? 100 microvolt, correct? Likewise, if RF is equal to say 100 kilo, right? Then your V output is equal to how much? If you multiply 100 kilo by 10 nano, that would be 1 milli, correct? And then if your RF is 1 mega, right? That would correspond to V output of how much? 10 milli, right? So that is the output, or I would say answer for these three cases. Let's take up another question. Okay, let's take question number 5 now. In question number 5, what we'll do is let's take this circuit and then tweak it a little. Okay, and then let me redraw this part. Okay, this is what? This is R naught, ground, right? And yeah, rest of the things are fine. So what we need to find in this question is a suitable value for R naught, right? Such that your output voltage of the circuit goes to 0. Okay, you need to find R naught such that V output goes to 0, right? I mean, you'll consider these three RF to R1 values. Let me copy them. We'll be considering, in fact, I'll copy this entire bunch. Okay, we need to find R naught such that VO is 0. Okay, how will we do that? Or how would we compute that? What is your R naught? It's R1 parallel RF, right? Your R naught is R1 parallel RF, right? And what? That is R1 RF divided by R1 plus RF. Okay, now for part 1, my R naught would be 10 kilo, 1 kilo divided by 11 kilo. All right, and that would be 909 ohms. Okay, or 0.909 kilo ohms, whatever it is. Similarly, second part, I'll have these values, right? So it would be 100 kilo times 10 kilo divided by 110 kilo. How much is that? That is 9.09 kilo ohm, correct? And similarly, for third part, R naught would be how much? It would be 1 mega times 100 kilo divided by 1 mega plus 100 kilo. That is how much? That is 90.9 kilo ohm. Okay, these are the five ones, and then we have, let's take another question quickly. So for the same circuit, uh, let's try to find the optimum value of R naught. Okay. If your bias currents are not same, suppose, I mean, my IB1 and IB2 are not same. Okay. Let me write that up. Find optimum R naught. If IB1 and IB2 are not same, let's take a particular case. Your IB1 is 6 nanoamps and your IB2, that is 10 nanoamps. Okay, then find the output voltage of the circuit for each case of RF to R1 values that are provided in question 4. Okay, again, we'll consider these set of values. Okay, now we need to find three values of R naught. Okay, so how shall we proceed on this one? Now the difference is IOS, which is the difference between IB1 and IB2, that is 4 nanoamps, right? And your V output, that would be IOS times your RF, right? And now we'll have three cases, right? When your RF is 10 kilo, when your RF is 100 kilo, and when your RF is 1 mega. Okay, for this one, my V naught will be 40 microvolt, right? For this one, V naught would be a factor of 10 would be multiplied, right? 400 microvolt. Likewise, for this one, it would be 4000 microvolt, or I can write it as 4 millivolt. Okay, so sixth is done. Now seventh question. Can anyone see when exactly was the recording started? Not sure if we can check that. Okay, let me draw the circuit for question number 7. Okay, for this particular circuit that is shown, find the phase difference between your input and output signals. Okay, assume you have a very large frequency, or take the frequency as infinite. Okay, and assume that your op-amp is ideal. Okay, find phase difference. Okay, take uh, at very large frequency, or take it as infinite. Okay, and assume op-amp is ideal. How many poles would there be? I mean, how many poles are there in the circuit? Anyone? There will be two poles in the circuit, right? And how much does each pole, or I would say, how much does one pole provide a phase difference in the circuit? One pole provides a phase difference of minus 90 degree, right? So how much phase difference would two poles provide? Minus 180, right? So each pole would provide a phase difference of minus 90 degree, right? Therefore, your phase difference is what? Minus 180 degree, correct? That finishes question 7. Now question 8. Let's consider the following circuit. Okay, suppose this is input Pi, suppose there's a capacitor here, there is a resistor here. Okay, this is R2, this is C2, R1, C1. Let's say this is what? VO. Okay, let's try to find the transfer function of the circuit. Okay, what you can consider is, you can consider R1 as 100 ohm. You can consider R2 as 10 ohm, and take C1 and C2 as 10 millifarad. Okay, just assume these are the values. Okay, meanwhile was someone. Okay, if I see recorded started from some 3 or 4. Okay, thank you. And okay, sorry, I was not able to see the chat in time. R1 not sure what R1 naught is. The delta T is TR, yes. Rise time was the delta T that I was talking about. How can we access the recording for the session? I mean, you had already given you the YouTube handle, right? You can either go there and wait for the lecture to be posted, or um, I guess NPTEL team would provide you on this problem solving session tab, right? There also you may be able to find the link. I'll again type the YouTube handle in case you're interested. Okay, so now, yeah, where were we? We were supposed to compute the transfer function for this question. Okay, so what will be the transfer function for this question? Be uh, this plus this. These impedances are in series, they will add up, right? And then it would be this and this in series, right? And these two are in parallel. So it would be something like this. If I write V naught by Vi, V naught by Vi would be uh, series of R2 and C2, right? That would be R2 plus 1 by SC2, right? Because you're trying to compute V naught across these elements R2 and C2, series combination of them, divided by. Now in denominator, it would be this in series with this, right? So I'll write again R2 plus 1 by SC2 plus what? Parallel combination of C1 and R1, obviously in frequency domain. Then how much is this? This is R1 times 1 by SC1 whole divided by R1 plus 1 by SC1, correct? I'll replace this by that. This is R1 by SC1 whole divided by R1 plus 1 by SC1, right? And which comes out as 1 plus S times R2C2, 1 plus S times R1C1, correct? And then it's 1 plus denominator would be, I mean, simplify this, this is the expression that you'll get after simplification. This is S, this would be R1C1 plus R1C2 plus R2C2 plus S square R1 R2 C1 C2. Okay, if now you substitute these values, V output by V input would be what? It would be uh, V output by V input would be 1 plus S, right? Because see, 10 milli is what? 10 milli is 0.1. 0.1 times 10 is 1. So this would be 1 plus s. Similarly, this is 1 plus s by 10. And this is 1 plus 1 plus 1 is 2s. Yeah, this would be 2s. Correct? Factored out with 1 plus 20. Yeah, I mean, if you simplify this, put in these values, this is what you would get. Okay, so this is my transfer function, VO by VI in S domain. Okay, that finishes this. Now, uh, does anyone have any question?
Hello, sir. Can you please explain what this S exactly is? Like, what is its physical significance?
Physical significance of S? Uh, Hello.
Yes, sir.
Okay. Has Laplace transform been covered as of now in the curriculum?
Till week two, it is not. And
No, I mean,
I,
let's keep this course aside. This is
oh,
something that probably would come as, I would say, a prerequisite in this course. Has control systems course been taught, or has signal and systems course been taught, or maybe
yes, signals and systems is done in the last semester, but we had
correct? Was
only a
Laplace
Z
transform
transform
taught
and
there?
Fourier transform. No,
Was
we
Laplace
didn't have.
transform covered there?
No.
Okay, it was not covered there. Uh, I'm assuming you will be an EC student, are you?
Yes, I'm in second year right now.
You are in second year right now. Probably either in second year or third year, uh, integral transforms would be taught in the math courses. Okay, but still, I'll give you a brief overview of what this S is. So this is a Laplace variable. So what we are trying to do is we are trying to write the frequency, write this whole impedance expression in terms of frequency. This S would have a real and imaginary part, or in general, I would say this is a complex frequency parameter. And the job of this would be to transform your time domain differential equations into simple algebraic uh, equations, right? If you will see this V output by V input, I wrote it in terms of what? In terms of S, which is frequency, although this is a complex frequency variable or frequency parameter, but this is in frequency domain. Okay, if you were to write this whole expression in terms of time domain, this wouldn't have been this simple or this pleasing. Okay, this would have been a set of differential equations. Okay, so I would say this is a mathematical tool that would make your time domain differential equations, or that allows you to convert them into algebraic equations. I mean, I'm trying to be very specific with regards to the application that we just encountered. Okay, but Laplace transform is way general than what I'm trying to define. Does that make sense?
Okay, sir.
Okay, and it would represent, if someone would tell you what does this S represent, you can answer him that this represents complex frequencies, okay, S plane in general, right? Where your this S would have a real part sigma and imaginary part omega, okay, and your this sigma usually denotes your attenuation and damping in terms of significance, okay, and your this imaginary part omega, it usually represents the oscillation frequency, okay. Because those
Okay,
are the
sir.
two things that you would be interested in a frequency response, right? And what else can I cover in this one? uh, yeah, I'll do one thing. Are you able to access the recordings of the lectures or the sessions that I'm taking? Hello,
No, sir.
you're not able to. Uh, but why is that the case? Will you not? Okay, let's do one thing. Can you present the screen? I'll turn off the screen
Okay.
broadcasting. Okay. Present the screen and open the NPTEL NPTEL platform. I'll tell you where can you access it. Yeah, there would be recording. Yeah, problem solving session January 2026 in the left side. Can you see that? Scroll down. Yeah, problem solving session. Yeah, click here. This will take you to a Google Sheet. Okay. Did you click on it? Or probably your screen stopped sharing
Yes,
for some
sir.
reason.
I found it.
Yeah, so there you'll have access to recordings, right? Uh,
Oh, yes.
the recording for this session would be week 3, okay? And in
Yeah.
week 3, I'll include a link on this Laplace transform from one of my previous sessions. Okay, I had taken
Okay.
a signal and system course, I guess, couple of years back. I'll include link of that particular lecture, and if you are interested, you can go through that. Okay, that will probably give you a brief overview
Yes, sir.
of
Yeah.
what Laplace transform is, and it may be helpful for others as well who are interested in it, because in frequency domain you will be quite frequently be using Laplace transform. So it's not a bad idea to revise the properties of Laplace transform or go through its definition uh, in half an hour or 1 hour. I mean, it would at max be 1 hour lecture. So yeah, that finishes today's session. So just uploaded. Okay, just a second. Someone, let me see which. So what is? Okay, this was your question, right? What is S? Explain that part again. Oh, Harsh. Okay, is this clear, Harsh? Okay, I guess you gave a thumbs up, so probably this is clear. What do you mean by this? Please just uploaded week 3 and week 4 problem solving link on Gmail. Uh, just a second. Let me. I mean the recording of the lecture. Okay. Uh, okay, this is my lecture. In case anyone, are you able to see the screen? Is the screen visible? It is, right? Yeah. So You can either first go to this channel, right? This is where I'm uploading the recorded lectures. So there is this analog circuits playlist, right? Open this one, week one, week two, and I'll have week three zone. Okay. And the lecture that I was just talking about, the signal system, is this one, week seven of this signal and system playlist. So in case anyone among you is interested, feel free to go through this. The Laplace transform and using Laplace transform and properties, these two lectures. Okay. Yeah, that's it. Okay, so I'll stop sharing again. So that finishes today's lecture. Does anyone have any question? Thank you. Thank you. I guess I'll. Okay, somebody raised the hand. Harsh, yeah, please go ahead. Exam pattern, you need to discuss that with NPTEL team. I'll not be, uh, I mean, making your question paper or designing your question paper. That is up to instructor. And if you need any insights into that, you can talk with NPTEL course team. Okay. Okay. I guess we don't have any more questions, so we can call it off. Thank you.